me take a look at the real definitions from trigonometry. Here is not working, so I have a little video. The way to find it is after I fix my menu, because I now have the wrong labels on things. That'll probably be tonight. If you go to today's notes, on the first page, there's a little link. That's not a link to the video. Well, there may be a link in here. Somewhere. You happen to have geometry stick pad, there's a nice animation, but most of you won't have that. Okay, I say the real definition of the trig functions. I think we've hinted, we looked at triangle trigonometry, and we looked at the sine and cosine. Sine and cosine is defined by a right triangle. So we have a hypotenuse, an opposite, and an adjacent, and we define the sine as the opposite over the hypotenuse, and the cosine sine of theta is opposite over the hypotenuse, and the cosine of theta is the adjacent over the hypotenuse, and so forth. The tangent function. But this only works for an angle between 0 and 90 degrees. And when I say between, I mean between. There's no sense of what sine of 0 and cosine of 0 are, nor of 90 degrees. So we're gonna go a little past that, and the way we do that, we start with a unit circle. By that I mean a circle with radius 1. And we look at angles in the standard position. That is, one of the rays is along the x-axis here, and the other ray, the terminal ray, is just, as before, it's just an angle from this ray. We take the counterclockwise direction as positive, so we can have negative angles going in the opposite direction. And we look at the point where this ray intersects the unit circle. Right? It has two coordinates, x and y. And we define the cosine of this angle as the x-coordinate, and the sine as the y-coordinate. Now let's first check. Let's make sure that that fits our previous definition. We have a hypotenuse, that's 1. We have an opposite, and we have an adjacent side. And we know the opposite over the hypotenuse, that's just the opposite. That's just this distance here. That's equal to the sine of theta for this triangle here. But this distance here is just what? That's the y distance. It's the y coordinate. Well, that's exactly what we're saying here. It's the y coordinate. Similarly with the adjacent side, right? The adjacent over the hypotenuse is just the adjacent, the length of the adjacent, because the hypotenuse is 1. And what did I write that? Yeah, where's that? Right. That's the cosine of theta. That's this x coordinate here. Take a good look at that. Let that seep in for a second. Defining the sine and cosine in terms of a circle, but at least from 0 to 90, it's the same thing as our triangle definition. Okay. This definition has some really nice advantages over the previous definition. For one thing, there are immediately some points that we didn't really know what to do with, some angles we didn't know what to do with. We look here at an angle of 0 degrees. All right, that's an angle where we have a starting ray and the finishing ray is in the same place. It's this point here. Well, what are the coordinates of this? Well, the x-coordinate, which is the cosine of theta, is just 1. The y-coordinate, which is the sine of theta, its coordinate is 0. Right? This point is 1, 0. So now we know what sine and cosine of 0 degrees is. Similarly, at 90 degrees, we have the opposite situation. The x-coordinate will be 0 and the y-coordinate will be 1. So we're already doing a little better. But this definition isn't limited to a 90-degree angle here. If we go a little further out into the second quadrant, in the first quadrant, we see something interesting happens. Well, our y-coordinates are kind of aligned with a point here in the first quadrant. Well, how are they aligned? Well, how does this angle compare with this angle? In other words, if this is still theta, what is this angle? All right, if those two angles add up to 180. A good guess, but remember these things move, right? So theta could go down to 0. 2 theta would be still 0. No, it's not. What we have is this angle and this angle added together is 180. We call this alpha. So I'm saying alpha plus theta equals 180. So what are those two types of angles? We call that when two angles add up to 180. Anybody remembers this from geometry?
Supplementary.
A good guess, an admirable guess, a very close guess. Supplementary. Right? Complementary is they add up to 90, supplementary, right, a straight angle. Okay, well that tells us something interesting. This angle and this angle are supplementary, but their distance above the x-axis to the y-coordinate is the same. So that tells us immediately that the sine of theta is equal to the sine of 180 degrees minus theta, its complement. Okay. On the other hand, let's look at its x-coordinate. Did I say that wrong again? No, that's the sine. What about its x-coordinate, right? As I move like this, here's one x-coordinate, here's the other x-coordinate for the complement. What's happened to that? Like I need some visual aids here. I have these two angles here, right? And I'm looking at this point on the x-axis. Right? I know these are complementary angles because they add up to 180. What's happening to this point as I move these things?
H is still 1, and the A is negative.
And I'm looking at here's the point kind of moving like this. I'm looking at the x-coordinate. What happens to the x-coordinate for these 2 points?
Doubles? Doubles?
Doesn't double. Well, I mean, remember this distance here, that's the x-coordinate, that's the cosine, right? This is the cosine of the complementary angle. So what I'm asking is what happens to the cosine of the complement of this angle, at least, between 0 and 90 degrees. In other words, look at this coordinate here. Let's give these coordinates a name here. Let's call this A and B. Well, we know the y-coordinate here is the same. It's still B. What's the x-coordinate?
Negative.
Negative A. Okay. Who said that? Thank you. Well, that tells me that the cosine of theta is equal to the minus cosine of its complement. All right, maybe too quick, maybe too early. Okay, well, the sine and the cosine are positive here, but that means that, I'm just going to draw this, plus, plus. What does that tell me about the sine and cosine here?
Negative.
It's negative plus. I mean, you can just tell that by thinking about points in this quadrant, right? The x is negative, the y is positive. What's going to happen down in the third quadrant? Negative, negative. Who said that? Did you say that? Yes, thank you. And finally, over here in the fourth quadrant, what happens in the fourth quadrant? Positive, negative. Okay. Does everyone know what I'm talking about here? Positive, negative, negative. I'm talking about the sines and cosines. You need a kind of a chart for that. Sine, cosine, first quadrant, plus, plus, second quadrant, plus, minus, third quadrant, minus, minus, fourth quadrant, minus, plus. Okay, so now we have this idea that a sine and a cosine doesn't have to be just positive, it could be negative. This has gotten too crowded, I guess I'll start over again here. There's something else that we can do with this definition. We can have an angle, if you recall from the other day, we can have an angle whose measure is greater than 360 degrees. Right? So let's call this 360 plus 45 degrees is 405 degrees. But we still have a definition for its sine and cosine, right? It's just still this coordinate. So we get this important result that sine of an angle plus 360 degrees is equal to the sine of that angle. Similarly, the cosine of an angle plus 360 degrees is still the cosine of that angle. Does anyone remember, we have a name for this kind of relationship a few days ago? It's a certain kind of function. I have a function f of x plus p equals f of x for some value p for all x. Does anyone recall the name of that kind of function? I use the letter p and I call this the period of the function. Is that called periodic? Yeah, it's a periodic function. Sine and cosine are both periodic functions with period. What's their period? Okay. Close. What's 360 degrees in terms of radians? 2 pi. Yeah. They have period 2 pi, or if we're using degrees as our scale, 360. All right, let's extend this just a little bit here. Let's take a look at these coordinates where the circle intersects the x and y axis. so that would be 180 degrees, 270 degrees, and then 360 degrees. So over here at 180 degrees, what are the coordinates? So they're -1 and 0. So, okay, let's just look at what's happened to the sine function. Right? It was 0. Up at 90 it goes to 1. Then it comes back down to 0. Right? That's the distance above the x-axis. So it's 0, moves up to 1, goes back to 0. Cosine, on the other hand, starts at 1. It's over here. The distance from the y-axis goes to 0, and then out to -1. All right, how about 270 degrees? That's all the way around over here. What are its coordinates? Yes?
0, -1.
0, -1. Okay. So now, again, let's look at the sign. It went from 0 up to 1, down to 0, now down to -1 again. And of course, when it gets back up here to 360, it's going to go to 0 again. And the cosine, right, starts at 1, comes into 0, goes out to -1. Now down here, it's going to come back to what? I have it written on the board there. It's going to come back to 0, right? That's its distance from the y-axis, right? 0. So the cosine comes back to 0, and then it goes back up again to 1. Right? Notice these two entries are the same because it's a periodic function. These are all kind of useful. This is useful information to absorb. All right. We're going to talk for a minute about, in this context, something called the reference angle. Every angle in this diagram, just pick an angle over here, has what's called a reference angle. A reference angle is an angle that's between 0 and 90 degrees. So reference angles are all over here in the first quadrant. If you have an angle in the first quadrant, its reference angle is itself. And so, just take note that the sine and cosine of the reference angle, an angle between 0 and 90, is the same as the sine and cosine of its reference angle, because they're the same angle. Over here in the second quadrant, the reference angle is a little different. Okay? If I have some angle here, let's say 135 degrees, its reference angle in the second quadrant is its supplement. So if my angle is 135 degrees, its reference angle is 180 degrees minus 135, which is 45 degrees. So its reference angle, of course, is still in the first quadrant. So why are we making this distinction? Well, if you look at the sine and cosine here, right? The cosine of this angle and the sine of this angle correspond with the sine and cosine of the reference angle. In particular, it's the opposite of the cosine and the same for the sine. So if I have an angle out here in the second quadrant, and I want to know its sine and cosine, I don't actually need to know the sines and cosines out here if I know all the sines and cosines from 0 to 90. So our old definition of sines and cosines using right triangles will still work. I can find a right triangle in this quadrant, and that tells me its sine is going to be the same, but its cosine is just going to be the opposite. I think, yeah, that's fine. Okay, what happens if I have an angle all the way over here in the third quadrant? All right, what happens to its, well, let's look at what happens to its coordinate. If I have some coordinate here, x, y, what are the coordinates of this point here going to be? Well, okay, let's look at this a little closer. This is my reference angle for an angle in the third quadrant. It's not the supplement anymore. It's what? I'm up here having blackboard amnesia. This is my angle here. How do I get back to an angle which is just the extension of this? Well, this is 180 degrees, right? So it's just my angle minus 180 degrees. Here's my reference angle. In other words, if this is reference angle is theta, and this angle is 180 degrees plus theta. Okay, so I have a line going through the circle. This is x and y. What are these coordinates? That's not obvious, is it? Nobody's saying anything.
Positive cosine and negative sine?
I'm just thinking in terms of x and y. I have some coordinate here, x and y. So what are these coordinates? Yes?
X and negative y?
Negative y is right.
Negative x?
Negative x, yeah. Remember, this is now the third quadrant. All the points in here are minus and minus, right?
Wait, so why is it in the first quadrant, why is it negative?
That was just in reference to this. I mean, the cosine, I could have, maybe if I wrote it this way, now I'm talking about the reference angle in this quadrant. All the points down here are minus, minus, clearly, right? All the points here are plus, plus. All the points here are minus, plus. And all the points here are plus, minus. So what I'm doing by picking a reference angle is I'm picking an angle whose sine and cosine are positive, but whose absolute value, whose value matches the absolute value in these other quadrants. So in particular, if I'm in the second quadrant here, I look at the supplement, 180 degrees minus this, and that's my reference angle. In the third quadrant, I get the angle by extending the ray, the line, and now my reference angle plus 180 is my angle. And finally, in the fourth quadrant, you can just think of it as this angle in the opposite direction. Didn't draw that very well. Hold on. There we go. Now it's just this angle, my angle here, in the opposite direction. I think of this as a negative angle. That's my reference angle. So again, my sines and cosines, their absolute values are the same, but down here I have a positive cosine and a negative sine. Okay. I want to enshrine that in a table, right? So first quadrant, second quadrant, third quadrant, and fourth quadrant. So my cosine of my angle, or the x coordinate, is positive. Right? It's positive in the first quadrant. It's negative in the second quadrant. It's negative in the third quadrant, and positive again in the fourth quadrant. So it kind of goes out. It comes in, goes negative, goes back to 0, and then it's positive. The y-coordinate, which is the sine, is positive here, right? Goes up. And then in the second quadrant it comes down. And then in the third it's below the axis, and again in the fourth. Now, let's talk about the reference angle for a second, right? The reference angle of my angle. In the first quadrant, it is my angle. If I'm in here, the angle I'm going to use to figure out the sine and cosine is my angle. If I'm in the second quadrant, right, that's over here, that's going to be the supplement, or 180 degrees minus my angle, my reference angle. I'm sorry, 180 degrees minus my angle. If I'm all the way over here, right, to get back to my reference angle, I just want to say theta minus 180. And if I have an angle all the way over in the fourth quadrant here, it's just the opposite of my angle. If you'd rather this be a positive value, you could just say 360 minus theta, right? Because every 360 degrees, these repeat. I don't get the feeling this idea has come through yet. See if I can go at this one more time. So I have a circle, It has radius 1. Does anyone recall what the equation of the circle must be? Anyone recall the equation of the circle at all? 2 pi is a number. I'm thinking about an equation.
H minus.
Yes?
X minus 1, H minus 1, H 1, X minus 1, and then times plus Y minus 1.
Okay.
Not 1, but just H and K, and then plus R equal to square or something like that.
Coming back to you. Yes, equals.
R squared.
Okay. Take a look at it again. There's almost there. Zoe?
The x minus h squared and y minus k squared.
Okay. So that's the equation of the general circle. My circle, h and k are 0, 0, right? So it's just x squared plus y squared equals, and my r is 1, so it's just 1. Okay. So that tells me something right away, which is x and y are both limited, right? X has to be less than or equal to 1, greater than or equal to 0. And y has to be between 0 and 1. Why? Well, we're squaring these. There's no subtracting here. And the sum has to equal 1. So it's limited to 1, right? So as I move my point around here, my x and y, right? The x and y's just can kind of move between 0 and 1. They can go negative, right? Because when I square them, you still get a positive number. So how do they do that? Well, let's just take the y coordinate. Starts here at 0, moves up, right? Reaches a peak at 1, and starts coming down, and now it's back to 0 again. We're going to take a look at a graph of that sometime in the future, but just think about that. As your angle moves around, the y kind of goes up and then down. But it keeps going down, right? As we move around further, it keeps going down. And then it hits -1, it hits the bottom, and then it starts moving up again. So that's just the y coordinate. The x-coordinate kind of does the same dance, right? Except it's what we call out of phase, right? It starts out, the x-coordinate starts out here at 1. As we move up, it gets smaller and smaller. Then it kind of goes out negative. And then it gets smaller and smaller again, back to 0, and then goes out again. So along its route, each time it goes through one of these semicircles, it goes from this axis to this axis, and then back, and then here. The x and y coordinates, if you just look at their absolute values, they each pass between 0 and 1. So if we're just looking at the absolute values, every time there's a point up here, there are 3 other points that share those numeric coordinates. If this is x and y, then over here we have what? We have negative xy. Here we have negative x, negative y. And here we have x, negative y. Well, these are the sines and cosines. So if I know the sines and cosines of an angle between 0 and 90, I'm going to be able to figure all these out by figuring out their reference angle. Okay? So for an angle over here, for a reference angle here for, say, this angle, well, what is that? Well, we know this angle and this angle here have to be the same. So, you know, this big angle that I want to know the sine and cosine for, its reference angle is still going to be theta. It's going to be 180 degrees minus theta. I didn't say that right. All right, ask me a question here. If you, or tell me what I just said. Somebody, please. This is everything's going to branch out from here in trigonometry. So I really want you to kind of see what I'm talking about here.
What was the question?
What am I talking about? All right. I'm going to give this one more go. I'm going to jump ahead a little. So again, I have a circle, radius 1. Let's talk about radian measure for just a second, right? If I have some angle here, theta, and I'm using radian measure, and the radius is 1. What's the length of this? What's the length of this arc here? Yes.
S equals the radius times theta.
Yeah. S equals r times theta. But what's r?
Is it the radius?
Yeah.
Oh, 1.
It's 1. So S equals theta. So this length here is my radian angle. Okay? So let's say I were to take, I'm going to create a new graph here. And in this direction, I'm going to go theta. So I'm kind of, this line here is kind of this length kind of stretched out in this direction. So as I move along here, I want to, what I want to graph here is the y coordinate of this point. So it's going to start at 0. And as my angle moves up, that is, as I move in this direction, I'm going to find my y is moving up. It's going to go up. It's going to go up until I get to pi over 2, or 90 degrees. It's going to hit here. It's going to hit a peak at 1. Then it's going to start going in the other direction. It's going to move down. So my angle kind of moves here, right? Again, I'm always, this length here is how far along I am. And then eventually, I'm going to get back to 0. Okay, I keep going, but now I'm moving down away from the x-axis. And then I move back up, and I get back to 0, and then I'm going to repeat. I know I'm going to repeat because this is a periodic function. All right, let's just mark some points here. This was pi, that's 180. It's 3 pi over 2, it's 270. It's 180, 90. And finally, we get back to the beginning, that's 2 pi, that's our period, or 360 degrees. Okay, so these y's are what? They're a function, right? They're the sine function. But if I pick some value here, I don't know, let's make believe this is 3/4. Right? I know between 1 and 0, I'll hit 3/4. So at some angle here, my sine is 3/4. This is in my first coordinate, my first quadrant. But as I move in this direction to my second quadrant, there's another point here at 3/4. Okay? Where is that? Well, this distance is pi, or 180. Here, I'm, some theta, right? Some angle that gives me a sine of 3/4. But here, I'm theta away from pi, so I'm 180 minus pi. Right? This distance here is 180 minus pi. Okay, I'm going to move forward. There's nothing over here. But down here, at minus 3/4, I run into the negative sign value again. Now I'm pi plus my angle theta, right? I'm in my third quadrant. And finally, if I keep going, I still get a negative value here. Now I'm in my fourth quadrant. But now I'm, what? This is now 2 pi, or 360 degrees, minus my angle. So the idea is you take these 4 points, 1, 2, 3, 4, and you say, well, what's the sign at those values? Well, all that information is wrapped up in this angle, the original angle, the reference angle. If I find the sine of this, I know the sine of this angle is the same. This is just the opposite, and this is the opposite. That's what a reference angle is about. On one hand, these functions, their period is 2 pi. They only repeat every 2 pi. But you can see every pi, it switches sign. It's almost like it has a period of, kind of an alternating period of 1, or 1 pi. All right. There's just a little more information here. There's a little bit more I want to say. Well, I were to go in the other direction, right, now I'm going negative angle here, you may notice something about the points over here. This is x and y. This is going to be negative x and y. Anybody see something? I guess that's not so visible in this picture. It's easier to see, instead of graphing the sine function, if I graph a cosine function, not so beautifully drawn. If you go back and think of transformations, or specifically reflections, you can see the cosine function is kind of a reflection across the y-axis here. For every point over here, there's a point over here. For every point here, there's a point here. Does anyone remember what we call that kind of function? In other words, a function where f of negative x equals f of x. That's an even function, right? Well, you have to think a little harder here. But what happens here is f of minus x is equal to minus f of x. That is, this point here, if I go minus, the function value is on the opposite side. So what's this called, of course? Odd function. All right, I guess I want to make one more point about this. Two more points. I kind of want to wrap this all into one thing here. I have some theta. It can have any value, right? Any real value. But it's a periodic function. So if I'm looking at theta values, it's like, we'll call this the theta axis, every 2 pi or every 360 degrees, the sine and cosine functions are going to repeat. So if I have some theta, and it's not between 0 and 2 pi or 0 and 360 degrees, I can always, it's out here somewhere, I can always move it to here by adding or subtracting some number of 360 degree values. That is, I have some theta, and that's equal to some alpha, which is between 0 and 360 degrees by adding or subtracting, I'm going to say adding 360 degrees times some integer. Kind of move it to where I can find the sine and cosines. Within this 360 degrees, right? 180, 360, 270, 90. I have my 4 quadrants. And between here and here, I can find the reference angle. That's going to tell me the sine and cosine. Right? And I can go one step further, which is now I have sine and cosine between 0 and 90. But as we saw a few days ago, we have these identities that say the sine of 90 minus theta is equal to the cosine of theta. This has to do with complementary angles. And likewise, the cosine of 90 degrees minus theta is the sine of theta. So really, if I want to know sines and cosines, I really only need the values between 0 and 45 degrees. I can find every other, the value of sine and cosine for every other value of theta. All right, I think I'm gonna stop there. We need a little practice doing this. I may put something extra on the homework assignment related to that. So.